Good morning, everyone. Thank you very, very much for having me here today. It's a very, very proud moment for me. I'm Dave Stewart. I'm a technical specialist in Rolls-Royce submarines, which for today effectively translates on the material and the process authority for a lot of the technologies and the materials that you're going to see in about the next 20 minutes or so. This is home away from home. This is Rolls-Royce in Derby. So as well as being the centre for the large civil engine Trent engines, it's actually where Rolls-Royce Submarines is based. For those who know Derby or your football, just in the top corner there is the Derby County football stand. So we're not too far away from the centre. Right, so what do? So we design, manufacture and provide the in-service support to the UK submarine fleet. Effectively, we've been involved since day one under the 58 agreement with the US. So effectively, we project managed that, which went into Dreadnought, and every other submarine from that day going forward and into the future is a Rolls-Royce pressurised water reactor. And we've been through a number of iterations of that, and we continue to do so to drive safety, availability, reduce costs, etc. The plan that we make is not too dissimilar to a standard pressurised water reactor. Effectively, we've got the primary circuit where we use the nuclear fuel to heat the water. The water then boils the water in the secondary circuit to drive the turbines. So what you'd see in sort of like Hinkley Point C, the Rolls-Royce SMRs, they're no different to effectively what we have. A central sort of pressure vessel, the reactions controlled by the control rods, lots and lots of pipe work, lots and lots of valves, pumps, the pressurizer, the steam generators. The material palette is really quite diverse. So we've got high alloy steels, low alloy steels, nickel-based alloys and cobalt-based alloys. So the traditional sort of structural materials that you'd expect to find elsewhere in the nuclear industry. So our story starts actually well over 40 years ago in the early 1980s with a problem in manufacturing. And manufacturing issues is actually one of the undercurrent themes through the rest of the talk today. So effectively what we had was a problem where the welders were struggling to develop deposit a cobalt-based wear coating down the bottom of those bores. The non-conformance rates were very high, well above sort of 50%, and really causing the business a lot of problems. So they looked for an alternative manufacturing means. Same material, just try and get the yields up. And what they did was they introduced a two-stage process based around powder and hip. So in the first part, we basically create a bar out of powder hip. So we take the powder, in this case of stellite 6, a cobalt-based alloy, and it's consolidated into the bar. The bar is decanned, and then effectively they take slices from that bar. We then effectively take a billet of steel, something like 316 austenitic stainless steel, and you drill the bore into it. You then drop the hard facing in, put the plug, seal it, evacuate it, and then it goes back into the hip vessel, where we effectively then use the hip to drive the diffusion bond between the hard facing and the structural steel. Once that's complete, then effectively you can go away and you can then machine the final component from the billet. Try and remember that, because we're going to come back to that in just a couple of slides' time. Having got the confidence in doing that and seeing how successful the process technology was, that then led into the first real sort of phase of the structural materials. So what we've got here is a four-phase strategy that the business put in place for high alloy steels, and specifically here, the austenitic stainless steels, starting with type 304 and then moving on to type 316. And the strategy effectively introduced a way of introducing the technology through increasing levels of risk towards the plant safety. So in the starts, it was sort of what we call the non-pressure boundary parts where we've got, if we did have a leak, then the leak would be limited and manageable, and then effectively parts where the parts become more engineering classified as serious, but you can isolate the plant, you can shut a valve and prevent the leak, up until the point where you get to the parts where you can't isolate the plant, and those are what we call the unisolable parts. And what you can see here in these slides effectively are examples of both the cans and the actual components themselves that we've done. And these are done with our partner MTC Powder Solutions out in Sweden. So the left-hand pair is a piece of pipework. So in the top you can see the can, and you will notice we've actually got a secondary piece of pipework that's coming off the large bore pipework there itself. So again, here we've got an opportunity to actually remove welds. And nuclear engineering, we love removing welds because they're a real sort of source of problem for in-service in the plant. Decan it, and that's the part that we're left with. The middle section, you might notice the top image from one of the brochures. That's a valve body, or a T-piece as we call it. You can quite clearly see the yellow capped off fill tubes where the powder is put into place. Again, sort of decanned, and you've got the valve body that's ready to go. The right-hand one, the bottom corner, is the largest component we've made to date. That's a pump bowl. It went in, it's about 8 tons, and represented some of the greatest wall thicknesses that we've done to date. And that was all sort of ready to go, and that's been through demonstration testing in the labs back at Rainsway. We have moved into other areas of powder metallurgy as well, but we've never quite managed to move away from hipping. So that original slide where I showed the 316 billet and the hard facing, we've now evolved that into an additive manufacturing stream. So what you can see now in the top left-hand corner is the 3D printing. So what we're doing here is basically 3D printing 316 to make the valve body, but we're leaving that recess. Then you move to the top right-hand image where you can actually see we've already printed the inserts of the hard facing. So the 3D body of the 316 is stopped, the insert is dropped in, and then the printing continues. And that's what you can see in the bottom left-hand corner. And on the build plate, we've got the integral test pieces that go into the hip as well. So we're still using the hip at this stage for the hip bonding of the hard facing to the 316 structural material. But we now end up with a much more near shape component with a lot less sort of subtractive machining that's required. It's not just the austenitic stainless steels, however, that we're interested in the high alloy steels, and we're no different to other industries in some regards as well. I always like the old sort of poem in the top left-hand corner, and I've seen it quite a few times in my career throughout sort of Rolls-Royce and elsewhere. It's never the big stuff that causes you the problems, it's quite often it's the little stuff. So if I translate that into the submarines, if I have a problem with the small stuff, then effectively, if I can't make my widget, I can't make my sub-assembly. If I can't make the sub-assembly, I can't make the component. I can't make the valve, I can't make the control rod drive mechanism. If I can't make the component, I don't have a plant. If we don't have a plant, the government basically doesn't have a submarine. So this has actually come to light us, because there is a certain adage in nuclear that's basically, if it isn't broke, don't try and fix it. And the problem is we've been making these plants since the late 50s. So what we're finding is that some of the ferritic and martensitic stainless steels that we use, and which we've been using for an awful long time, and which do quite niche applications for us, we're actually seeing now a risk of obsolescence. So effectively, as industries in the sort of the foundation, sort of the steels industries move on, some of the alloys that we're reliant on effectively become a problem to get hold of. So what do? Well, we actually looked at using the option of using powder hip, effectively as raw material supply. And what we did is we looked at sort of 4 steels, 3 of which I've shown here. And I've tried to do an analogy according to Google that the average male in the UK weighs about 85 kilos. So what you can actually see is that for a boat on its own, some of those are a sort of equivalent to less than 1, significantly less than 1, or equal to sort of a couple of people's worth of material. If I then ramp that up into a dreadnought type class for 4 boats, I actually still, in some instances, have less than 1 person's worth of material that I need in order to satisfy the demand. So this is one of the things that we've been looking at. The post from the bottom right-hand corner is one of the things that we've tried to be getting a good handle on. Life is quite easy for us when we make our austenitic stainless steels, because we effectively make either 304 or 316L grade, and then we do nitrogen atomization, so we effectively get 304LN or 316LN for free. And they're well-established grades, and everyone understands what the nitrogen does. If you move that across to ferritic or martensitic stainless steels, that might be a different question. So we've got some work, this is actually with Imperial College, where actually we've been using atom probe to really understand where the nitrogen is going at the sort of at the atomic level, and working up from there the implications for what it might mean for the materials. And some of those might actually be positive as well. You can see that top one's a 12 chrome ferritic steel, so it's actually just bordering actually being stainless. whereas nitrogen is actually known to improve the pitting resistance. So yes, it might give a problem with the phase transformations, but it might also give us an advantage in the corrosion behaviour. The nickels, I won't touch too much on, but effectively, yeah, we've done them. This is some work we presented quite a while ago looking at a parametric study on both 600 and 690. And we've actually got Enkino 625 now in production for applications within the plant as well. So nickels, we've effectively done that journey, and we'll continue with the 690, but we're pretty much over the line in terms of 625. Which brings us to the final one, and in some regards, the one we've left to last because it's the hardest. So over the decades and over the plants, we have used low alloy steels for our major vessels, and they represent significant volume of the large forgings that we do. And we've evolved over the plants in terms of both the materials and the manufacturing method. So we're at the point where today, where effectively we have large forgings, cylindrical, that again allows us to remove welds, that we basically make in sections up at Sheffield Forge Masters, which then effectively come down to Derby, where we assemble and clad. When this project was initially launched, there was serious concerns again about the fragility of the large forging supply chain. So the question was asked, what about powder? Can you effectively do a powder low alloy steel for these sorts of applications? And we're not the only ones who are asking that question. Our early work, like everyone else, showed, as expected, getting the strength is no problem. The powder hit material is really, really good. And on the left there, you can effectively see the tensile data across the temperature ranges. The crosses and the plus minus, they're the two batches that we had made. The ASME requirements are aligned. So we're well extending sort of on the strength. Elongations, reduction in areas, they're all fine as well. So everything's looking really good. The problem that we and everyone else had was with the Sharpie impact energy data. And this gives us an indication of the toughness, and that's a really critical parameter for the nuclear pressure vessels. And unfortunately, we're not even close, and neither was anyone else. And everyone believes that it's down to the oxygen content that effectively that impacts the impact energy. So there are various things that you can do, and one of the things that we found was actually through the Euro PM 2021 conference. There was a very nice paper by, again, one of our partners, MTC, with the research organisation, Schwerin, who looked at doing 316 and a different grade of 508 steel. And they showed significant improvements. So what we've done is we've mirrored that, but on the specific grade of 508 that we're interested in. And again, what we find is it doesn't really hurt the tensiles at all. There's a very small improvement in the elongation in the reduction areas, but they were generally fine anyway. So good, but nothing really sort of anything of concern there. Certainly nothing detrimental. On the toughnesses, however, the sharp is it's chalk and cheese. So really managing to get rid of the oxygen, suddenly we've now got powder hit material that we can say is the equivalent of the forging route. And that really is where we want to be. So this is one of the options that we've got now in order to maturing this technology in order to be able to start to implement it in plants. And there are other people who are sort of looking at it. We may not go down with the hydrogen stripping route that was demonstrated. We've got one or two other sort of development routes in progress at the moment where we think we'll end up in the same place. So at some point, we'll probably decide which of the methods. But the key thing is now, 508 is doable and you can get the properties. Whilst we've been trying to get the properties, we've actually been continuing our manufacturing development, because one of the problems with the 508 is the oxygen and keeping it sort of away from the atmosphere at all stages until it's in the cans. So these are some of the demonstrators that we've made over the recent years. The one in the sort of top left, we call that the small vessel demonstrator. It's about the height of a person, but it's got an awful lot of features that are effectively characteristic of all of the vessels that we actually need to capture should we take this technology forward. And then effectively what we've got is sort of a strategy that means we go and make bigger and bigger bits. So what you can see in the top images are the two halves of the small vessel demonstrator, and in the bottom you've got what we call the ring section demonstrators. So they might be actual part of a full-size vessel that effectively then you could join, and the technology we've been looking there is electron beam welding to join them together. This is development work, I do stress, and we haven't been quiet about the failures, trying to share. There's a really good sort of camaraderie in the nuclear industry about sharing best and, in this case, worst experience. So we have shown where we've had problems. So I thought I'd show them again, because one of the pictures is quite cool. So one of the problems we had was effectively the can leaked. And we had the atmosphere from the argon hip vessel, unfortunately, go in. So what you can see in that bottom image effectively is the can material. It's relatively thick. And then you can see lots of lovely 508 powder that unfortunately hasn't consolidated together. So we managed to track down where the leak was, and you can see there it's a hole in the weld. We also actually got quite an interesting problem with the internal can, where it actually debonded during the cool down cycle because of the CT mismatch. So again, that's something that we might need to give some thought about whether which is the most appropriate can material. Because if that happens earlier in the cycle, again, that could give us some quite considerable problems. So again, like other people, we've had the same thought. So if I can make pretty much all of my other components out of powder, and I can now make my vessels out of powder, that opens up an opportunity to get rid of dissimilar metal welds, which are really one of the banes in nuclear industry. So what we've done effectively is looked at, can you effectively make a transition piece? So for example, if you came off of the powder HIP 316 pipework, could you transition into sort of a powder low alloy steel, and then you've got a low alloy steel to low alloy steel weld, and everything is really quite easy for you. What we did is we did some fairly fundamental work trying to understand the metallurgy of the system. And we did that work with the University of Manchester, and this is just an example showing effectively how the microstructure changes as you have basically an alloy that's pretty much iron and not a lot else. And then you put it next to 316, which has an awful lot of something else in it, and what actually goes on. And we found some really interesting results, which hopefully Manchester will get around to publishing in the near future. But we're now actually seeing how that can be applied to some of the other systems that we've got, because like everyone else, we actually have quite a lot of dissimilar metal welds in the plant. So to try and sum up then our story over the last 40 years, effectively what we've been able to do is do a sort of an incremental journey through all of the materials and through sort of pretty much all of the components that gets us to where we are today, but effectively means that when it comes to the plant, effectively doesn't matter if it's a high alloy steel, a low alloy steel, a nickel-based alloy or a cobalt-based alloy, you can do it out of powder. Thank you very much indeed.